Welcome to your exam strategy session. Today, we're treating your Cambridge IGCSE Mathematics paper like a high-stakes courtroom trial, and you are the lead barrister. You see, to secure top marks in syllabus-0580, you can't just memorize formulas. You need to build an airtight case, evidence, argument, and an undeniable conclusion. Today, we're decoding set notation and Venn diagrams. Whether you're tackling core or extended, understanding sets is literally learning the language of mathematical logic. It's how examiners test whether you can organize data perfectly, or if you're just guessing. So how do we actually turn this abstract alphabet of symbols into a visual tool that destroys complex logic puzzles? Let me introduce you to two types of students. First, there's Alex. When Alex sees a word problem, he overloads. He just dumps all the raw numerical facts onto the page with absolutely no analysis. Then there's Sam. Sam rushes. Sam doesn't read the subtle differences in the notation, misses the core requirements, and bleeds marks. We are constantly bombarded with raw data in these exam questions. Without a bulletproof system to organize how these different categories relate, you're just staring at a wall of noise. Set notation is your analytical framework. It's the strategy that turns chaos into clear, undeniable evidence. Here is our case file for today. Number 1, we'll establish the facts by defining sets and elements. Number 2, we'll organize the evidence with subsets and the universal set. Number 3, we are visualizing the argument with Venn diagrams. Number 4, we'll analyze intersections and unions. And finally, number 5, we'll prove our case by solving a complex, multi-layered set problem. Let's get to work. Section 1, defining sets and elements. Let's establish our absolute basics. What actually is a set? In mathematics, a set is a well-defined group of objects or symbols. The crucial phrase here is well-defined. In a courtroom, you can't have ambiguous evidence. It's exactly the same in Cambridge Math. There must be zero ambiguity about whether something belongs in your group or not. A set could literally be the countries in Africa, like South Africa, Namibia, and Egypt. It could be infinite, like the set of all natural numbers. It can even be the specific coordinates on a line. The individual items inside these defined groups, well, those are called the elements. And this brings us to our first crucial piece of mathematical shorthand. Mathematicians, much like top lawyers, love efficiency. Instead of writing out the phrase "is an element of" over and over again, we use this special curved E symbol. It firmly states that a specific piece of evidence belongs to a set. And, just like a massive "do not enter" sign, we simply cross it out with a slash to declare that it does not belong. For instance, the number 3 is an element of the natural numbers, but -1 absolutely is not. Getting this grammar right is step 1 to not losing silly marks. Section 2, subsets and the universal set. Before we continue, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's talk about subsets. Think of subsets like a set of nesting dolls. If every single piece of evidence in your first group, let's call it set X, is also found perfectly inside your second, larger group, set Y, you have a subset. We denote this by using an elongated C shape with a solid line underneath it. If set Y is defined as all fruits, and set X is mangoes and bananas, then X is absolutely 100% a subset of Y. But here is where students like Sam rush and make critical errors. Look closely at the notation. There is a very subtle distinction we need to make. That horizontal line under the C for subset means the two sets could technically be completely equal. Set X could hold the exact same elements as set Y, but a proper subset, which drops that little line underneath, means the set is strictly smaller. It lives entirely inside the main set, but it definitely does not contain every single original element. Recognizing that difference is often worth a full mark on paper 2. Let's ground this with a concrete example. Let's say we have set A, which consists of 3 students, Winnie, Natalie, and Emma. We can break this group down into smaller categories. A group of just Winnie and Natalie? That forms a proper subset. Just Winnie on her own? Also a proper subset. But here is a mind-bending mathematical rule that examiners love to test. The empty set, represented by a 0 with a diagonal slash through it, is considered a subset of all sets. Think of it like an empty room. That 0-element state is a possibility in absolutely every scenario. Never forget the empty set. Now, before we start mapping out our data, we need to define our jurisdiction. We need a canvas. In set theory, that overall boundary is called the universal set, represented by a capital E or sometimes a squiggly symbol called Z. It contains every single possible element we care about for a specific problem. Nothing exists outside of it. And if we define a specific set within that universe, everything else, literally everything in the universe that is not in set A, is called its complement. We write that as A prime with a little apostrophe. It's the mathematical equivalent of saying all remaining evidence. Section 3. Visualizing with Venn diagrams. Enter the Venn diagram. This is where your case becomes visual. Instead of just listing numbers in curly brackets, which gets confusing incredibly fast, we can map them visually inside designated circles drawn on our page. That rectangle around the outside, that represents our total jurisdiction, our universal set E. And those circles inside, they contain the specific elements of the sets we've defined. It's clean, it's organized, and it's exactly what Cambridge examiners want to see when you're structuring your logic. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS. And turn on all notifications so you never miss our weekly exam strategy sessions. Now, back to the case. If every category in life was perfectly separate, Venn diagrams would just be a bunch of isolated, boring circles. But data is messy. Real life is messy. What happens when a piece of evidence belongs to more than one set at the exact same time? What if a number is both a multiple of 2 and a multiple of 3? This is where the real analytical work begins, because our circles are about to overlap. Section 4. Intersections and unions. We are now giving names to the specific geography of those overlaps. Here are the 2 most critical operations you must master. First is the intersection, symbolized by a downward-facing arch. Think of intersection as the strict, uncompromising and. You only get into the intersection if you can prove you exist in both circles at the exact same time. Second is the union, symbolized by an upward-facing U. The union is the generous or. It scoops up absolutely everything. If you're in the first circle, the second circle, or the middle overlap, you are part of the union. Time for an interactive challenge. Let's test that strict intersection rule. Look at the data on screen. Set P contains multiples of 3 up to 18. Set Q contains even numbers up to 12. I want you to quickly scan this data. Which numbers survive the strict intersection rule to live in that overlapping middle region? We are looking for the overlap that matches. Scan it. Got it? Only the numbers 6 and 12 exist in both lists simultaneously. So, P intersection Q is simply the set containing 6 and 12. Notice how carefully we must cross-reference the data to find the truth. Now let's reverse the strategy and look at the generous union. Here we have set X and set Y. To construct X union Y, we simply combine all the elements from both sets into one giant master list. But here's the trap that students fall into. We never ever write duplicates twice. Notice that the numbers 3 and 14 appear in both sets, but they only appear once in our final union list. The union grabs every unique, distinct piece of data from either set. It's comprehensive. Section 5. Solving complex set problems. This is where we bring it all together to secure maximum marks. Take a very close look at this exam-style scenario. We have a universe of 31 total students in a class. The data tells us 22 study physics, 20 study chemistry, and 5 study neither. The ultimate question: how many students take both subjects? Remember our student Alex from the beginning? Alex just takes the raw numbers and adds them up. 22 plus 20 plus 5 equals 47. But wait, the evidence clearly states we only have 31 students in total. Alex just fell into the classic double counting trap. This apparent mathematical paradox means some students are being counted twice. They are hiding right there in the intersection, and we have to extract them. We are going to solve this mystery systematically, using 4 logical steps that bridge our visual Venn diagram with pure algebra. First, we clean up the edges. We know 5 students study neither subject, so they sit completely outside our circles, but still inside the universal rectangle. 31 total, minus those 5, means exactly 26 students belong somewhere inside the physics and chemistry circles. That's our active union. Next, we label our unknown target. We let X represent the students hiding in the intersection, taking both subjects. Now we build the equation. By substituting our unknown intersection X into the middle of the diagram, everything else falls into place. If 22 total study physics, then the region that is physics only must be 22 minus X. Think about that. If 20 total study chemistry, the chemistry-only region is 20 minus x. When we add those specific isolated regions together, the physics-only, the chemistry-only, and the intersection x in the middle, they must perfectly equal our 26 active students. The logic is flawless. All that's left is the execution. We just simplify the algebra. 22 plus 20 gives us 42. Then we have a minus x, a plus x, and another minus x. Those first two cancel out, leaving us with a single minus x on the left side. So our equation simplifies to 42 minus x equals 26. A quick mental swap tells us that x must equal 16. We have found our hidden intersection. The undeniable conclusion is that exactly 16 students take both physics and chemistry. If you plug that 16 back into the Venn diagram, every single region balances perfectly to 31. Case closed. Our source material provides this vital piece of examiner wisdom. The information can be entered in a Venn diagram in stages. This perfectly summarizes the winning strategy. When you first look at a word problem, it looks like a tangled mess. But sets allow you to break down complex data into manageable, solvable stages. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. You know, you don't actually have to be sitting in an exam hall to use this. From the algorithms recommending your next playlist based on the exact intersection of genres you listen to the way we categorize medical symptoms or filter search results online, sets are absolutely everywhere. It is the hidden architecture of logic, just waiting for you to decode it. The next time you see overlapping categories or confusing data, I challenge you to draw the circles and find the intersections for yourself. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep analyzing, and I'll see you in the next session.